Following heat treatment, the barrel portion is turned almost to final size, leaving only a grinding allowance, but the journals are left plain until after the hardening operation. Trepanning a central hole ensures a satisfactory distribution of residual stresses resulting from the drastic quench used in the hardening process. It also permits visual examination to ensure freedom from defects which might lead to failure during final heat treatment or during service. Ultrasonic testing establishes that the roll is free from defects in regions which cannot be examined visually, as only sound forgings are passed forward for hardening. Heating for the hardening process is carried out in vertical furnaces specially designed to ensure uniformity of temperature. The journals are carefully protected to prevent their being hardened when the barrel of the roll is quenched. On withdrawal from the furnace, the roll is transferred to the high-pressure water spray tank for quenching. The final hardening process is a highly specialized operation and the most critical stage of roll making, since the very hard working surface must be allied to an ability to withstand the various stresses arising during service. After hardening, rolls are tempered to establish the surface hardness appropriate to service requirements. Tempering consists of reheating the hardened steel to a temperature usually in the range of 100 to 200 degrees centigrade. Following tempering, checks are carried out with the diamond pyramid hardness tester to confirm that the correct hardness has been obtained. A Shore scleroscope is also used, mainly to determine uniformity of hardening, although the diamond pyramid hardness test is essential for exact hardness determination. The good performance of a work roll in a cold rolling mill is greatly dependent on the surface hardness and depth of hardness. To obtain a suitable depth of hardness, several factors must be taken into account. First and foremost, a stress problem is involved. When a solid piece of steel is heated to a uniform temperature and then water quenched, the outer layers cool very quickly, and as the inner layers cool, they do so against the restrictions imposed by the outer layers. Thus, a complicated triaxial stress system is set up. The magnitude of the stresses is very high, with tensile stresses in the region of 60 to 70 tons per square inch set up at the center of the roll. If a hole is bored down the center of the roll and water quenching introduced there also, the stress system is quite different. The dangerous tensile stresses have now substantially decreased in value, but more important, they have moved to the mid-radius position with both the surface layers and the bore in compression, eliminating the possibility of fatigue failure from the bore surface in use. This is the basis of the classical hardening technique. To avoid brittle fracture, as shown here, consideration must be given to the depth of hardness by selecting a steel analysis giving a hardness at the mid-radius part of the roll low enough to accommodate the triaxial stresses. The depth of hardness curve varies with the analysis of the steel, particularly the carbon content, and also the temperature from which the roll is hardened. As the depth of hardness increases, the hardness at mid-radius, where the hardening stresses are most critical, will also tend to increase, and this puts a practical limit to the depth of hardness. Induction hardening is sometimes used, but has certain disadvantages compared with the classical method, particularly in introducing a greater tendency to spalling. Our final graph illustrates the hardness distribution in an induction hardened roll, indicating a possible reason for this premature failure. Material immediately under the hardened layer has been close to the hardening temperature, but has not been high enough to transform to austenite. On cooling, it will be in a very soft condition and may be insufficiently strong to support the hardened layer. Also, the need to use a high surface temperature to compensate for the short heating period can lead to coarse grain size and poor mechanical properties at the working surface. Spalls in induction hardened rolls can originate in this very soft region. Despite these disadvantages, induction hardened rolls do feature in Firth Brown's production program, and as one of the first roll makers to install induction heating equipment, we can claim many years of experience with this process. As has been indicated, it is not recommended for work rolls in heavily loaded mills, but is ideal for the production of auxiliary rolls, such as leveler rolls and bridle rolls, since it gives a greater depth of hardness and a more uniform hardness than flame hardening. It can also be used for rolls requiring extensive internal drilling operations, such as those used in linoleum and plastics production. Following hardening and tempering, the rolls are ready for final machining. The journals are turned to grinding size, followed by the machining of flats and keyways on this duplex miller, which has tandem cutting heads working on both sides of the roll simultaneously, enabling this precision work to be more speedily carried out. The form of mill coupling and the bearing assembly governs the design and shaping of the driving end. Our grinding section is experienced in the grinding of a wide range of sizes and types in fully hard and semi-hard rolls. Initial rough grinding removes scale and decarburized layers, while the finishing operations are carried out with wheels of finer grades. After extensive periods of use, most work rolls can be successfully re-hardened for further service, but reheating and requenching inevitably produce distortion. The main problem is to correct the portion of the roll to which the bearings are fitted. If this portion has to be repaired, it has become common practice to use metal spraying. The majority of rolls treated in this way have given entirely satisfactory service, but this type of reclaimed roll should be handled more carefully than an untreated one. Free from inclusions, and the new double melting processes have to be utilized. In the electro-slag process, steel is remelted through a fluid slag which absorbs or disperses the non-metallic particles in the steel. The atmosphere is excluded throughout the operation, and the final product is very high-quality material, containing only very small, widely dispersed inclusions. Firth Brown can provide a wide range of grooved rolls for hot rolling. In the hot rolling of ferrous and non-ferrous material in bar form, the high resistance to fracture of forged steel rolls makes their use essential where deep gates and high loading are involved. This is particularly so in the case of stainless steel and high-strength alloys. In the past few years, cooperation between Firth Brown and various rollers of copper rod has led to substantial improvements in the quality of the final product and to greater tonnages being obtained from these grooved rolls. It is true that forged steel rolls, particularly the high alloy type which are recommended, are more expensive initially than the cast rolls previously used. However, when the tremendous improvement in rod quality and greatly improved groove life with fewer roll changes are taken into consideration, the roll cost per ton of copper is substantially reduced. Furthermore, since the rolls are of uniform hardness throughout, the groove life remains constant over the life of the roll. Where the design permits, it is also perfectly feasible to machine a smaller roll from the scrap rolls, and so secure further life at a minimum cost. Rolled sheets of aluminium, brass and copper are produced in large tonnages in the form of coils or in single sheets, and it is essential that for the hot and cold rolling processes, only rolls having a very high surface hardness and excellent surface finish should be used. The rolling of precious metals used by the jewelry and electrical trades is yet another example of the variety of purposes for which forged steel rolls are used. The Firth Research Laboratories, serving the Firth Brown group of companies, was one of the world's first industrial research organizations and can claim among its many successes the discovery of stainless steel and the provision of the special steels required for the original Whittle gas turbine. The continual research and development carried out by this organization is of inestimable value to our roll-making processes. Facilities such as these enable Firth Brown, in cooperation with the roll user, to develop the special characteristics required for any particular application. Here, for instance, we see equipment for the automatic counting of inclusions in steels, an essential part of high-quality production control. From the rolling mills of the world comes an endless stream of material to be made into a wide variety of consumer goods. Motor cars, washing machines, refrigerators, aircraft, ships, razor blades, coins, kitchen utensils, toothpaste tubes, milk bottle caps, and oil drums are just a few of the many applications for rolled materials. Rolled sheet in the form of tin plate is fabricated into the essential tin cans for our everyday commodities. 3,000 million containers per year are produced by this plant alone, and it can be seen that the roll maker plays an important part in the lives of us all. Care and attention to detail at all stages of roll manufacture is maintained in the packaging and dispatch. Protective coatings, together with special wrapping and crating, are the final operation before rolls leave the Firth Brown works for customers in more than 50 countries throughout the world. The development of Firth Brown rolls is greatly assisted by the cooperation received from users, who provide detailed results of their experience with rolls under a wide range of operating conditions. It is essential that this close collaboration should continue, and the experience accumulated to date, together with the resources of research and technical staffs, is made freely available to all who have an interest in Firth Brown forged steel rolls.